So we continue with solitons and smoothings. So I apologize for you to Nikita for using this word smoothing. I didn't capture how he calls it otherwise, and anyway, it's in our papers called this way, the smoothing. So I'll keep it. And just to tell you why I think it's a good name, you should imagine that you have a corner, and then you start to smooth it layer by layer, but still your corner is made of some discrete matter. So from the far away, it would look like smooth, and but close up, it will still be discrete. So that's my intuition for like the what it really means, the smoothing. And like what's important is that for those corners, there is some limit in a sense that you cannot smooth it more when it's already smooth enough. Okay, let's also.
But what you mean by a limit is that there is, in a certain scale of discreteness, the best possible smoothing that you cannot.
Yes, exactly. There will be some best possible smoothing.
But at that scale, have you changed the scale?
No, nothing changes because well, you'll see, you'll see exactly what it means because otherwise, well, without context, it doesn't make too much sense. But anyway, so to answer the question of Ernesto from the previous, no, from the first talk, the superharmonic function is really the function which has a non-positive Laplacian. That's I've checked it. It's like this. And what's important about the space of all superharmonic functions is that it's closed under taking the minimum. So in here you can say, well, that's something tropical already. So this space of superharmonic functions is something like tropical algebra. You can take minimum, which is some kind of addition tropically, and also you can take sum, which is some kind of product tropically. And you'll see that actually our main examples of superharmonic functions are actually tropical polynomials, so this is not a coincidence. Okay. Then a bunch of definitions. For a function on the lattice, we denote DEF, the deviation locus, the locus where your function is has non-zero Laplacian. Okay, then here comes the main preliminary definition for the smoothing. Let's read it very carefully. So for a given superharmonic function and a natural number n, denote by theta n of f the set of all functions such that every function there is superharmonic. It's between the function and this function minus n, and the locus where this function and f are different belongs to some finite neighborhood of the deviation locus of f. Okay. So these are functions which, in a sense, are same as f at infinity, but can be less by controlled amount of values, somewhere close to where the Laplacian is non-zero. And now the next definition is that the pointwise minimum of all functions in theta n is called Sn of f, and this is called the n-smoothing of f. Okay?
Nice definition, very nice definition.
So, and then we will be interested in the cases when this sequence of smoothings stabilizes. So when you cannot go further. So that's the main theorem of today, and I'll tell you the very next, very last slide, one before the last slide. What other cases we know of this theorem? But for now, let's take the simplest non-harmonic but superharmonic function, which is just a minimum of a constant and a linear function. And the claim is that the sequence of smoothings stabilizes. And here it's crucial that these P and Q are coprime. If these two numbers are not coprime, if PQ is the not primitive vector, then the smoothings can go forever. And what really happens, for example, if you have something like a minimum of 0 and 2x, right? You can do something like minimum. So I'll write it down just. So for example, you have minimum of 0 and 2x. This was your f.
I cannot see what you write. I cannot see what you write.
Is it too small?
No. It's just in my screen. Only the bamboo paper screen is showing up.
I'm writing exactly.
Ah, yeah. Okay. Yeah. Sorry, it just was delayed. Sorry, it was just delayed.
So, okay. So if you take example when this theorem fails, take f to be equal the minimum of 0 and 2x, for example. Then Sn of f, and here I'm not sure, but I think it should be something like minimum of 0 of x minus n and 2x. Is it right, Nikita?
Yeah.
Nikita?
Yeah. Okay, yes, it's right.
So you see, what really happens that we can do the smoothing by really cutting the corner. So if there is some smaller monomial in between the two, then we can cut it indefinitely. So we had a corner like this, and then we cut it. So I'll show you. So we had a corner like this, and then we cut it indefinitely. But in the previous conditions, we cannot do that. There are no such monomial, which is smaller than this 0 and px plus qy. Okay. Anyway, so this smoothing at which we stabilized is called the canonical smoothing of f.
Okay, very good.
Then what we observe is that the Laplacian of such canonical smoothing is always greater or equal to -3. And the argument why it's the case is very easy. So if not, there is some point where it's less or equal to -4, then we just remove one value at this point, and the function stays superharmonic, and also it's smaller than this canonical smoothing, which is supposed to be the smallest among functions which are the same at infinity and are superharmonic. Make sense?
It does make sense, yeah.
Okay, and therefore we can do the following. We can add 3 to this Laplacian of theta f, and it will take values 0, 1, 2, 3, because it's superharmonic and because it's greater than -3, this Laplacian of theta f. And the theorem, which I will sketch, the proof of which I will sketch, is that this is really a soliton.
Fantastic.
Okay. Okay. So this is the plan. So not the plan, but like periodic, it's trivial. Why the previous state is periodic? Because in the definition, definition is symmetric, right? It respects the symmetry of the function of this minimum of the constant and the linear term. So it's obviously periodic. In our paper, we even written a proof. Like, imagine it's not periodic, then we can make this canonical smoothing even smaller by taking the minimum of this canonical smoothing with itself translated by the periodicity vector. So, but anyway, this is a triviality that is periodic. Line shaped, it's also trivial because by the third condition in the definition, all smoothings differ from the original function only in the neighborhood of where Laplacian is not zero, and where Laplacian is not zero is exactly a line. So it's line shaped. And now the hard part is actually it's movable. That this state, when you apply a wave from some big territory, moves in some predictable way. And so here what we'll do the following. So when so let's take the territory where this canonical smoothing is constant, okay? And we show that applying the territory, applying the wave from this territory results in doing the canonical smoothing of a function where we increase the constant part by 1.
Very nice, yeah.
You see it. And this, at the level of the line, it results exactly in moving it by the complementary primitive vector. Complementary in the sense that with PQ, this P prime, Q prime gives a lattice basis. Okay. So that's how we prove it. And now I explain in slightly more details how it's done. So we need the following lemma. So which I don't prove. It takes some effort, but not too much. That the smoothings are monotone. So if you have a function g which is less or equal to than g prime, then n smoothing of g is less or equal than n smoothing of g prime for all n. And this clearly implies that theta f prime is greater or equal than theta of f, just because f prime was greater than f, because f prime is the result of adding 1 to the constant part in the minimum. And so what we prove is that the wave toppling function, so the toppling function which arises when you apply the wave from that territory, is exactly the difference between these canonical smoothings. And this would imply the theorem. So now it gets slightly more technical. So first we get one inequality, which is just a version of the least action principle. It's easy to see that if you take the state, which is this Laplacian, this state, Laplacian theta f plus 3, and then you add the Laplacian of this difference, then it's a stable state just because, well, you can cancel the two Laplacians, and then it will be 3 plus Laplacian of the theta f prime. This is stable. But what you need also for applying this least action principle is that the value of the difference is 1, at least at some point. From where you send the wave. And this is guaranteed just because in this territory f prime is bigger by 1 than f, exactly by 1. And so you can apply least attribution principle, which gives you this inequality, and this is one inequality. The other inequality will follow from the fact that adding the canonical smoothing of f to the wave toppling function coincides with f prime outside the neighborhood of the deviation locus. Why is that so? Well, on one side, it's 1, it's clear. You do a toppling at every, at least at every vertex of the territory, and you don't do topplings on the other side of the presumable soliton because of the previous inequality. It tells you that it's 0. So we know that on the two big territories where your canonical smoothing is linear and where it's constant, it's the same as f prime, this sum of the wave topplings function and theta f. And also it's superharmonic, which is also clear because the resulting state when you add 3 is stable. And so by just by definition of the canonical smoothing theta f prime, it should be smaller than this function. Okay, so this is very formal proof to give you the flavor of what's going on in this paper on solitons and smoothing of superharmonic function. And actually, this is the smallest proof of substantial content in the sense that it's already non-trivial, but still it's presentable. There are quite a lot of things which would take hours to explain. So, for example, the theorem about stabilization of the smoothing is already much harder.
But it's the same.
It's same spirit.
The same sort of arguments. It's like the same chess, just more complicated place in the same chess.
Yes. Well, with maybe some with a couple of extra moves, maybe, but the style is similar. Okay. Anyway, so now we come to what I've promised to show you, the size of the PQ soliton. This was the last slide of the previous exposition. So now we know what is a PQ soliton. We can approach the question of its size. And I recall how we state this question. We know that since it's periodic, it makes sense to do the push forward of this soliton to the cylinder, and we denote it by phi tilde, and then compute the net defect on this cylinder. And the claim is that for PQ soliton, the total defect from all three is p squared plus q squared. And we denote it by dpq. Okay, how is it proved? So take as a function the minimum of 0 and this linear function qx minus py. This is PQ periodic. So it's non-smoothness locus or Laplacian non-zero locus is a line going in the direction PQ. And we observe that for big enough domains on the lattice and some given number n, the defect, the sum of defects on these domains for the function g and for its smoothings are the same. And this follows from a very general fact, from a very general identity, which is some kind of Stokes formula, which tells you that integrating Laplacian on some domain is something like integrating it over the boundary.
Yeah, makes sense.
Yeah, and so since we know that the function and its smoothing coincide at infinity, the defects of one can be computed from the defects of another. Okay, and so yeah, to compute the defect of the soliton, it's enough to do it just for the original function, which is the minimum of 0 and the linear function. And so this is very easy. That's what we do. We pass to the rectangular 0p times 0q. So this is smaller than the fundamental domain from the cylinder, apart from one point. So we shouldn't count twice the corner 0, 0, and pq. And for that reason, I say that the defect is the same as taking the minus Laplacian over the rectangular with the vertex PQ removed. We compute the value also at this vertex is minus PQ, and we apply again same identity to the problem of computing the Laplacian on the rectangular. We evaluate it as the sum over four sides of the rectangular. I do it once again very carefully, and we see that the contributions from two sides are just 0 because of this picture on the left. So this is how G looks on the right below. It's 0, on the left above it's linear, and so the first two summoned are 0, and the second two, they always give the same value. What is inside of the sum? In the first case, it will be just p, repeated p plus 1 times, and the second, the last summoned, it's q, repeated q plus 1 times. So we put all together, and finally we get p squared plus q squared. Okay, so this is very concrete, very simple computation, but here we really used the smoothings. So we used the relation of the soliton to this minimum of two functions. And yeah. Okay, and as I told you, this p squared plus q squared is exactly the weight of a pQH in the definition of the tropical symplectic area. And I decided to tell you slightly more about that.
Fantastic.
So, since it's for the YouTube, I've chosen to tell just the shortest possible definition of a planar tropical curve as a locus of non-smoothness of some tropical polynomial, which is something of the form minimum of a tropical monomial, and deliberately I write it as some kind of monomial, so as AV plus Z times V. In tropical terms, minimum would mean summation, plus would mean multiplication, and scalar product would mean taking power. Here V is some lattice vector, and A is some subset of such powers, if you like. Okay, and a tropical curve consists of straight edges, each of which has a rational slope. And for a finite h of lattice length alpha and a primitive direction pq, so primitive means that it's the smallest integer direction going parallel to this edge, and also multiplicity. And here I really don't want to speak much about multiplicities, but some of the edges on a tropical curve can have multiplicities, and we'll talk in detail about that next time. So anyway, the area is proportional to the p squared plus q squared times alpha, where alpha is the actual length in SL to Z length of this segment, and m is multiplicity. So if your segment is just from 0 to pq, then it's simply p squared plus q squared. Alpha is 1 in this case. Okay, and now and when the area, the tropical symplectic area, makes sense only for finite tropical curves, or rather, well, compact. If you have at least one unbounded edge, then it will be divergent. So, okay. So let me write it that it's tropical symplectic tropical symplectic area. This is just the sum over all edges in some bounded region in R2. So you have some tropical curve, whatever, and then you take some bounded region and you compute it only there. And now, like what's very important about this area for the applications and just for in general is that it's invariant under small deformations or just deformations. So if you perturb a little bit your curve in such a way that it's perturbed only inside of the domain and you don't touch the boundary, then the area of the two things will be the same. And in the sand pile level, the analogy of this fact is the following. If you send a wave from somewhere in the sand pile domain and the wave never reaches the boundary, then the mass is unchanged. Then the total weight, or if you like, of the two sand piles, one before applying the wave and the other after applying the waves, are the same. So and this is not a coincidence, because from what I was trying to explain right now, this tropical symplectic area is really something like sand pile defect is a really symplectic area. And on this slide, I am telling you just in few words why we call it symplectic area. And for this, we need to recall that tropical curves, they come as degenerations of complex curves. So this is very standard for people who've seen tropical geometry. But for those who've never seen it, this is probably not the best slide to learn about this stuff, but still I felt obliged to include this, otherwise it's incomplete. So anyway, so C star is C without zero, complex numbers without zero. Log T is the logarithm with base T, which is coordinate-wise logarithm of the absolute value, or other way around, the real part of the complex logarithm. And for a family of algebraic curves where T is somewhere near infinity, consider rescaled amoebas and which converge to some tropical curve C. And every tropical curve can be obtained in this way, and this is one of the good ways to see tropical curves as limits of complex curves. Now we take this omega, which is ID log Z1, ID log Z1 bar, plus ID log Z2 bar, wedge ID log Z2 bar. It's the standard symplectic form on this algebraic torus, C star square. And let's be the bounded convex set on R2. Then the following statement holds. If you compute the usual symplectic area, so on the left you have this symplectic area of a piece of this algebraic curve at the preimage of the domain, then asymptotically it's the same as tropical symplectic area, up to 4 pi square and log T. So in a sense, tropical symplectic area computes the coefficient in the top asymptotic for the degeneration of the usual symplectic area.
When you said every tropical curve, what about this issue of realizability or not?
Every curve on every planar tropical curve is realizable.
Planar, of course.
What did I write? So anyway, that's just why I also included this slide is because I still think that it's possible to find an analog of the sandpile model in the complex geometry. So in this series of talks, we are moving towards understanding the tropical counterpart of sandpile model, but still, I think there might be something interesting before the tropicalization, purely at the level of complex curves. And from what we learned from these last two slides is that the analog of the sandpile mass should be symplectic area. And probably it's not complex geometry, probably it's symplectic geometry. And well, I can tell a few more words in the sense that this should be thought not as algebraic curves, but rather as holomorphic curves with boundary on some Lagrangian tori. And then it makes sense the minimization as some kind of Steiner problem. Like the version of the least mass principle. But this is still incomplete. After many years, we still don't understand, I think, what happens in the symplectic geometry side. Tropically, we have some understanding. Symplectically, I think something is still missing. Okay. So that's more or less the last slide, and then I wanted to include some bonus slide. Here we didn't prove the theorem about the stabilization of the smoothings, and this is an important result, and it's not easy. And people conjectured that Soliton existed, but this is really establishes the proof that they exist. The same result holds for more complicated functions than just minimum of a constant and a linear function. And what we really need for understanding tropical curves and sandpiles are at least minima of 3 linear functions, which we call triads, especially in the case when this tropical curve given by 3 rays is smooth, and this is guaranteed by the condition this P1 Q2 minus P2 Q1 is equal to 1. So we definitely need this. We need the local models for vertices, for smooth vertices of tropical curves, but we need even more. We need we need also nodes, and we need deformations of nodes, because in what will follow, we'll see sometimes we have a perfect control. We are dealing with a discrete analog of a tropical curve, and the tropical curve was smooth. And then we do some deformation, and suddenly our curve stops being smooth. But it's nodal. And so we want to control this situation. So this is the picture on the right below. So here, sometimes when we do the deformation, the curve becomes nodal. And we want to control also this. And this is exactly the last case when we know that theorem works. In our paper, it's simply called node, but it's not correct. It is node, but only for specific choice of the coefficients C1, C2, C3. It's even more. It's all possible deformations of this node, and this is exactly what we need. Okay.
Yeah, I understand.
So what I told you is for these two cases, the proofs are similar, but they are much harder than for an edge than for a soliton. But still, it's possible to do. I don't know. Maybe we could do it sometime later. For the proof of the main theorem, understanding the proofs for triads and nodes is not essential, but it's still, I think it might be useful to come back to deeper understanding of that. So today we've seen, we can say, a tip of an iceberg, or really those solitons, those triads and nodes. they deserve much more attention and better understanding, especially from the speaker side. So if you are willing and if I'm prepared, we could do it some other time. But next time we will do more of tropical geometry. Especially, I'll try to explain why in these deformations you don't see higher singularities than nodes. I told you that we do deformations and sometimes the curve stops being singular, stops being smooth, but why it cannot become more singular than just nodal? And
Very
it can.
interesting.
It can become, but not generically or not terminally. So there are some deformations which result in something much more severe than just nodes, but we can avoid all these cases. Okay, and the bonus.
Somehow you can remain within the modular space, the compactification of the modular space, the ordinary compactification.
Yes, and that's very important for the proof. Exactly. And luckily, these were exactly the cases where we can prove this theorem about the canonical smoothing. Otherwise, the thing wouldn't work.
Very interesting.
Okay, and then the bonus slide. So in that paper, which I used for today's discussion, there was some vague conjecture about movable states. That vaguely a movable state, so something which moves in some linear direction with applying the wave. It's either a soliton or triad, maybe also on some background. But here I just show you an example of some more complicated state, which is still made of solitons and triads, and which is still movable. So if you apply a wave from the right, it will move to the right without changes. And then you can construct many more examples of this type. But all these examples will be deformations of some singular triad.
I see what you mean. Wow.
Okay, just so that was just something I found when I was preparing to today.
Very nice, beautiful.
Okay. So any questions?
Well, thank you very much.
We stop recording.